Today's lecture will finish up talking about form-active structures by looking at some fun stuff, exotic structures that use the very simple form-active principles that we've talked about to achieve sort of incredible spans and really unique shapes. We'll look at two principles in particular, one called tensegrity, which comes from Bucky Fuller and Kenneth Snelson's experiments in the 1950s, and then we'll spend a little bit more time on pneumatics, air-inflated structures, and we'll talk about why those are form-active in at least some ways, and what we can do to make them exploit form-active principles to achieve really kind of incredible spans. First, you might remember that when we were talking about suspension structures, we talked about being worried about uplift, right? That these structures are so light that we have to accommodate not only the gravity loads and the wind loads or lateral loads that we're used to accommodating, but we also have to worry about the possibility of the wind actually sort of spilling over a flat roof like this and literally lifting the roof up. And we had talked about a couple of ways that we use cable structures to absorb not only gravity loads, but also these uplift loads. One of them is to use stabilizing structures, so cable trusses that run both directions and therefore are able to provide tension resistance both to gravity loads and to uplift loads. So here, this example, you can see that there are cables with two curvatures. One that is a positive curvature, a frowny face, and one that's a negative curvature, right, a smiley face. And we can imagine that the roof load under normal circumstances is here going to get carried by the negative curvature cables. This cable is going to go into tension. It has compression struts here that are going to transfer the load of the roof down to that cable. The cable is raised up by these compression masts on either side. Remember, in most tension structures, we have a compression structure that's helping it to do the work. And then here you can see the backstays that are both holding the masts up and then transferring the weight of the roof through the tension in the cable all the way down to foundations. But note too that the roof itself here has within it these cables that go in the other direction. And so you can imagine that if a wind comes along and spills over the front, creates an eddy that actually is trying to suck the roof up off of the ground, then this secondary set of cables will go into tension and will actually hold the roof down, right? So we're designing one cable system that's holding the roof up and one cable system that's holding the roof down. And that's important because uplift can impart very high loads into roof systems, just like gravity or lateral systems can. So we call this shape a lenticular shape from the same Latin root that gives us lens. And you can see why. It has curvature in two directions, so it looks very much like the cross-section of an optical lens. Half of those cables at any given moment aren't really doing much, but they're there and they'll get sort of called into action as and when the situation shifts, when we get uplift instead of just gravity load. And here are some ways we can do that. That example is what we call a coplanar cable, so curvature in two directions. And you can see that we can either have them sort of top to bottom or bottom to top, right? We can make, here's the lenticular shape we were just talking about. Here is a shape where we've actually got the lens kind of turned inside out. We can also do this with cable ties, or we can calculate or even engineer the dead weight of the roof so that we can be assured that no foreseeable wind is going to provide enough uplift to actually pull the roof up. This is called a dead load strategy. And if we're building a roof out of, say, concrete, it's a perfectly effective way to do it. We're relying on the weight of the concrete to basically pre-tension, to put the cable into tension before any external loads get put on it. And if that roof is heavy enough, we can imagine that there would be no foreseeable wind that would be strong enough to reverse the load on the cables, right? So that cable is always going to be in tension because the roof is actually going to work against the uplift that a wind spilling over the edge might give it. And we looked at a couple of famous examples of this. Alvaro Siza's Expo Pavilion in Lisbon, where you can see there's the very, very shallow catenary shape. We talked about the huge buttresses on either side that take the weight of that, the thrust, the inward thrust of the cable arch, and transfer it to the ground. And also famously Dulles Airport. And here again you see the catenary curve. You see the hangers that the cables are strung from, and then here in this kind of construction sequence, you see at the end they're pouring a relatively heavy concrete roof that guarantees that there will never be any uplift. And this again is a process, in this case called pre-tensioning, putting so much tension into the cables that they will never, in any foreseeable wind, experience a reversal, right? It'll never try to go into compression. And we know, of course, that cables don't do compression particularly well. The other way we can think about this, though, is that we can combine arches and membranes, or we can combine membranes in two different directions to create what we call double curvature. And what this means is that no matter what load is hitting our structure, there will always be a load path, whether it's a system of cables or a system of cables and arches. We can always imagine that there is some load path that will carry whatever load we're putting on it, whether it's gravity or lateral or uplift. So in this example here, where we're combining compression arches and then a network of tension cables that are sort of stitched together into a fabric, you can imagine that under ordinary circumstances, you can see that negative curvature there, the smiley face. That curve is going to help channel whatever weight we put on the roof into the arches, and then the curve in the opposite direction is going to channel that load down into the ground. But let's say that we have uplift, right? Let's say that we have a significant storm coming through and the wind blowing over the top of this membrane structure is trying to basically pick the tent up off of the ground. Well, then notice that if we turn in the other direction, we have curvature that is now positive, right? A frowny face. And what that means is that any uplift is going to get carried in tension by the cables running in that direction. And that's actually going to keep the fabric structure like down on the ground. So the arches and the cables going in two different directions basically accommodate whatever loading condition we can think of. And if you look carefully at this for a while, you can see that there's always curvature in at least two directions. Even if we take a plan cut of the structure, we find that we can, if we look carefully enough, we can find a curve in the right direction so that the membrane will take a tensile load in that direction. And this means that this doubly curved membrane can take gravity, can take uplift, can take wind load from any point on the compass, and therefore is a very efficient, very effective structure. Right? It's safe because it acknowledges kind of all conditions, and it also can respond to those conditions in multiple ways. Right? There are lots of load paths that can carry that load. When we design pure tents without arches, note here we've got compression masts, but the rest of the shape of this roof is composed entirely of fabric. You can see too that we have curvature in two directions. We have a very, very long negative curvature there along the cross axis. And then going in the other direction, you can just see that there's curvature going the opposite direction. So a negative curvature in the short direction of each tent module. And again, what that means is that the tent will be able to carry wind loads, uplift, lateral loads in any direction, either through the very long curve here, right, that's basically holding the structure down, or through the long curve here that's holding the structure up. And if we cut plan sections, we'd find that there are curves in the membrane structure that can accommodate wind load from any direction as well. So double curvature is one of the ways that we have to fight unpredictable loads on these very lightweight and very vulnerable structures. One kind of exotic combination of form-active elements and vector-active elements is what's called tensegrity. And this basically uses straight cables, which go in in vertical and horizontal directions, to accommodate gravity loads by separating, just like a truss does, those loads into tension and compression elements, and then using the network principle of vector-active systems to carry those loads to anchorages on the sides of the span. Tensegrity structures are these kind of weird, almost kind of uncanny looking things because it's very, very hard for our eyes to figure out where the load path is going. But essentially you can see here that it's essentially a triangulated truss, but we're relying here on the kind of curved nature of the plan to complete the triangulation. So here you can see one triangle with a compression strut, two tension cables, and because it's a triangle, if we fix that point and that point in space, then the third point will be kind of automatically fixed. We can keep doing that, kind of raising in each sort of orbit of the tensegrity structure up until we've achieved a fairly tall structure. And again, if you kind of zoom out, you can imagine that the tension on the bottom is clearly doing some of the work of bending. It's these cables on the top that I think are misleading. We expect from what we know of trusses to see compression elements there. And in fact, all of the compression is being taken by these vertical separators that are turning the entire roof structure into a three-dimensional set of triangles, and therefore basically carrying the bearing load by channeling those loads down into the bottom rank of cables. You can see these are very, very lightweight, also very easy to assemble. You start with a single suspension cable, and then you gradually attach the compression elements to nodes in the cable until you're able to sort of build up the center of the roof. And once in place, once everything is triangulated, this is fixed. It's a very flexible structure, but you can see also that it has these two load paths, right? It has cables that are coming down that are supporting the weight of the truss, but it has cables going in the other direction up, and you can sort of sense a kind of positive curvature here to those cables that holds the roof down in the event of a big wind. Here are a couple of tensegrity structures that maybe are a little, in some cases, maybe easier to understand. So here you can imagine that each one of those squares is turned into an element of a truss in section by those compression elements, which come down through actually the middle of the square bays. Here maybe it makes a little bit more sense. You can see that the tension cable on the top, the tension cable on the bottom. And then here, Kenneth Nelson, who was a student of Bucky Fuller's and came up with this principle, made a career of designing sculptures that use the tensegrity principle. So here is one module where three compression elements are connected by cables that triangulate them in space. So their ends are all fixed relative to one another, and this becomes a three-dimensional truss where all of those triangles are stable, and therefore the overall form is stable. Even though to our eyes it looks like these three sticks might fall down at any minute, each of their ends are stabilized relative to one another. So with that, let's turn to maybe the most exotic form-active structure that we'll get, a pneumatic structure, which in some ways behaves like a surface structure, but we'll kind of talk about it, get into it as a form-active structure. So thinking about pneumatic membranes really as arches. There'll be arches obviously in more than one direction, but the fundamental principle that we want to think about is to think about pneumatic structures as basically cable structures or arch structures where the logic is completely inverted, so that instead of thinking about hanging a cable or supporting an arch, we're actually going to think about a cable that we're putting energy into, we're putting a load into, to just like in the dead weight cable structures that we looked at a few minutes ago. Here we're doing the exact opposite. We're pre-tensioning cables or fabric by injecting pressurized air into a system. And that air pressure, just like the dead load of the heavy roof cables, that air pressure is going to make sure that membrane, that pneumatic membrane, is always in tension. And we're going to inflate it. We're going to put so much tension into the membrane that no matter what load we put on it, whether it's a gravity load or a wind load or an uplift load, part of that membrane is always going to be in tension. And it's never going to go into compression, even in situations where it might look like that. The energy that we're putting in terms of or in the form of pressurized air is going to make sure that membrane never leaves the state of tension. So here are a few student experiments. Pneumatics are fun because you can go to the hardware store, you can buy a few clear drop cloths and some duct tape, and if you have a fan, you can build a pneumatic structure. So here a couple of kind of classroom exercises in building these things. And you can see some of them you have to kind of crawl into, right? You have to find a way to get into it without deflating the thing. In other cases, you can see that there are basically these giant air pillows. And the air pillows mean that the pneumatic principle is contained within the structure itself, and we can walk in and out without having to worry about whether we're letting the thing deflate or not. These structures sort of emerged as a military technology in the 1950s. The American Air Force in particular wanted structures that could shelter radar and missile installations in the Arctic. And so they commissioned these fabric structures that could be delivered by helicopter, blown up by fans, and provide shelter against the elements that would allow people to work on missiles and radar and things within. You can see also they're fragile enough, thin enough that things could get out as well. And this, of course, is both the great advantage of pneumatic structures and also their greatest drawback, right? They're very, very lightweight, but also very fragile. A lot of the early sort of pioneering work in pneumatics came from a German engineer named Frei Otto, who looked at soap bubble films and realized that a soap bubble was basically a very, very small pneumatic structure. The molecular structure of soap molecules means that they are always trying to contract. They're always trying to enclose a volume with the smallest possible surface area. And so the simplest soap bubble is just a sphere. That's the shape you get when you try to find the smallest surface area that will contain the largest volume. And what Otto realized was that there's a principle in nature that nature loves triangles as much as structural engineers do, and that when soap bubbles meet, the tension in the soap surface will always try to equalize the angles between them. And so you will always get these recurring 120-degree angles, or as close to 120 degrees as the spherical geometry will let you get. And that'll pretty much define, for the amount of soap that you have and the amount of volume that you're trying to contain, that will always determine the geometry of the thing. So if you look closely, you can see all of the intersections here have these 120-degree angles that represent the equilibrium of three spherical surfaces pulling with equal tension. And so these are very, very efficient. They use the least possible material, and when inflated, the circular geometry here is actually right. The dead weight of the membrane, in this case soap, is really trivial compared with the force being exerted by the trapped air. And therefore, instead of looking for catenary shapes or parabolic shapes in pneumatic structures, we really are looking for circular shapes, or to be more accurate, spherical or hemispherical shapes. Otto did a lot of experiments, a lot of kind of pretty radical proposals for things like greenhouses out in the German countryside. Here you can see a proposal for a pneumatic membrane that would enclose an agricultural plot that would allow them to control the temperature a little bit during poor weather. These were super popular in student projects in the 60s. They were kind of a radical technology, and they matched the sort of sensibilities, the radical political and cultural sensibilities of students, especially in the late 60s. You can still buy pneumatic furniture today. But you can see also a real fascination with these kind of emergency shelters that came out of military technology, lifeboats, things like that. And also a sense of real kind of playfulness, right? That there is also clearly a family of kind of pool toys and things like that that are probably the way we understand pneumatics best. As I mentioned, there are kind of two different types of structures, types of pneumatic structures. One that we call air supported and one that we call air inflated. In both of these cases, we're using energy to inject air into the pneumatic at a higher pressure than in the outside world, so greater than the 15 psi or so. That's a natural atmosphere. And in doing that, what we do is we put an equal pressure on every square inch of the membrane, if we've designed it right. And that uniformly distributed load perpendicular to the surface everywhere, and therefore exerts a consistent tension force throughout the membrane. If we make this force high enough, we're doing kind of exactly the opposite of those heavy concrete roofs, right? We're putting the membrane into pretension, not by loading it up from above, but by loading it up from within, and putting so much tension into that membrane that whenever we get a force that's trying to put it into compression, whether that's gravity or wind or whatever, the pressure of the air inside is going to overcome that and make sure that the membrane is always in tension. There are two general ways we can do this. One is we can simply make one giant balloon, right? A balloon that we walk into where the pressure on the inside is much greater than the air pressure on the outside. And you can see that this works exactly like a cable structure, but kind of flipped upside down. We have the pressure coming from below pushing out, and therefore we're going to have forces. We're going to have forces in the foundations that literally hold the membrane down and keep it from sort of pulling in and up. So tension foundations instead of compression foundations. In an air inflated system, we're looking more at pillows than balloons. So these arches here are all self-contained pneumatics. We inflate them individually, keep fans running to each one of them, but the pressure is actually contained within the arch itself. So this is literally a pillow beam, we might call it. And note a couple things. One, we have pressure that's working on both the inner and the outer surface. Note, too, that when we walk into this, we don't need to be concerned about losing the pressure in the pneumatic, that we don't need the revolving doors or the airlocks or the things that keep an air-supported or balloon structure up. In both of these cases, we'll often rely on cables, both to help hold the system down, right, but also to kind of collect and absorb the stresses in the membranes. You can imagine that over a long distance, the 300 or 400 feet that some of these things get to, the stresses would build up in ways, or they would move the membrane around in ways that would be both dangerous structurally, but also maybe not so desirable functionally. And so this network of cables attached to anchorages in the ground helps both to hold the thing down, right, to keep the air pressure from lifting the thing up into the air, but also allows us to control the shape somewhat that even under windy conditions. We'll stop there for the moment. We'll look in the next lecture at some of the details of these pneumatics, some of the pros and cons, and we'll also look at a couple of case studies of really big structures that have used these principles to enclose long span spaces that in some cases are kind of world record in terms of their spans.